Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So hi, I'm Asela. I'm going to talk to you about models for temporal event streams. This is, of course, work with a bunch of really great collaborators. So to start off, what do I mean by temporal event streams? I simply mean streams of events that have both a timestamp and a label. So here's a little cartoon I have of kind of a simple one where there's two kinds of labels, blue and red. And over time, these events occur, and some of them are blue and some of them are red. And so this is a cartoon view of a bunch of kinds of data that we actually care about, like search query logs, web page visits, Facebook check-ins, data center event logs. So for example, with search queries, instead of having just blue and red, we'd have a whole bunch of different possible labels corresponding to different queries, but they all have timestamps. And so what we want to model is what events are going to happen and when they're going to happen. And this would depend on what's happened in the past and when it happened in the past. So it's not just the what, but the when. And I'll keep repeating this, hoping that you'll eventually see how this is different from what's been done before. Now, why do I want to do this? Well, one reason to do it is to simply understand what's going on in these systems. So for example, imagine that we have a data center and all the machines in the data center log all the errors that they spew out, and that I have some kind of automatic management system that also logs everything it does. And the data center is humming along, and there are some errors, and the management system decides to maybe install patches on some machines and reboot some other machines and re-image some other machines, and eventually, every so often, it gives up, and somebody's pager goes off, and they come in, and they get in a little golf cart, go to the machine, and they actually futz around with it, and that process is actually really expensive. So I might want to know, why are we sending a technician to a particular machine? And if I look at the error logs on that machine, what I see is a complete mess. A bunch of different events happening over time. And at about 3 o'clock in this case, we send a technician to the machine. Well, why? Well, you could painstakingly go event by event and try to figure out what's going on. Or if you had a model that understood the dependencies between these events, it could show you that these are the two key events in the past that caused the technician to go there. The C drive failed. The automatic system tried to re-image the machine, and that didn't help, so the pager went off. Another thing you might want to do is try to predict the future. So say that you're running a search engine, and you have users issuing queries, so you kind of have an idea about what they're interested in. And an advertiser comes to you and says, I'm an advertiser in the health and wellness industry. Can you please show this ad, plaster it on the top of, say, Hotmail, but just to people that are actually going to care about health and wellness. And I don't want to wait till they issue the query. I want to show it to them the whole week, before or after. You want to figure out which of your users are actually going to care. So say you've been watching a couple of users. One of them searches for Elizabeth Edwards' will. The other one searches for pellet guns. And then they search for camo. And the next day they search for online education. And then they search for Valentine's and they misspell it, and then they immediately correct themselves. Then the other ones, a few days later, searches for snow pictures, and then Versailles Palace. And this is when the advertiser comes to you and says, show your users this health and wellness ad. And you're sitting there scratching your head saying, well, who should I show it to? Right? So how many people here think that we should show the ad to user A? Only one person has an opinion. Okay, 2. User B. You guys are maybe right, maybe wrong, but let's see what happens. The first user searches for Amazon, and then for chairs on sale, then adoption, and the Dave Thomas Foundation, which I had to look up. It actually works in adoption. And then user B, you guys were right. Exercise equipment and high blood pressure. Right? So what we'd want is models that can actually make these predictions. Maybe we can crowdsource it, right? But then show the ads to the right people. And one of the challenges when we're trying to build these models is the data is really bursty, right? So when the person corrected their spelling on Valentine's, so when they searched for pellet guns and camo, those queries came within tens of seconds of each other. And then sometimes we didn't see him for like, I'm assuming him, maybe I'm wrong because of the pellet guns and the camo, but for 5 days, 4 days. So the time spans can vary from seconds to days. Now, this is a challenge if you're using discrete time methods like DBNs, HMMs, or Markov chains, because, well, you could ignore the times, but I think it's pretty easy to argue here that the times are kind of informative. Or you can decide to sample every 10 seconds or so as not to lose any information. But now you've got these long stretches of tens and thousands of steps where nothing happens. And this makes it really hard to learn the dependencies involved, and it makes it hard to do inference or forecasting forwards over tens of thousands of steps. So a different approach is to do the modeling directly in continuous time, and there's been a bunch of work that has tried to do that. And we actually tried a few of these. Now, it turns out that a bunch of these methods restrict the kinds of dependencies you can have on the past. And it wasn't clear whether the assumptions that were chosen for those particular models actually matched the data we care about. Another problem is that we want to operate on Bing query logs, which are a little big. And a lot of these methods don't scale very well to that kind of data. And so what we want is, first, to make less restrictive assumptions about the data, and second, still be able to scale to these huge data sets. So what I'm going to tell you about is a technique we came up with to do that using a modeling technique involving conditional intensities. So I'm going to take a little detour to explain what those are. So to be a little more formal about the data, you can mathematically what the process we're looking at is a mark point process. It's a point process because it's generating times. And it's marked because each time is marked with a label telling you what happened at that time. Now, you can write a likelihood for a marked point process forwards in time, predicting the time and the label of each event given everything in the past. Now, what's really cool is marked point process theory tells us that we have this conditional intensity representation for any marked point process. Now, those of you who've looked at Poisson processes might, if you squint a little bit and hide the conditioning on history, it looks a lot like a Poisson process. But let me quickly give you a sketch to convince you that that representation is possible. Say you just had a density over times. You could then define the intensity as the density divided by 1 minus the cumulative distribution function, the CDF. Now, the derivative of the CDF is the density. So multiplying the top and the bottom by the denominator, you get this differential equation. And now you plug through your calculus, and you find that the density is just an exponential, just with a time varying rate. Now, if you have a time and a label, what you do is you look at the density of the time and the distribution of the label given the time, and you define the per label intensity as the overall intensity times the conditional of the label. And now you plug in. And this is exactly the same form we had before, except you need to condition on history and pull the sum and the exponential out and make it a product. And now we have this form. Well, OK, mathematically, you might say, OK, I can go check the math, and he's probably right, but what does this mean? Right? So I'm going to give you some intuition about what this representation means. So let's go back to a cartoon world where we only have two kinds of events, blue and red. And we don't have any events yet, so the history is completely empty. And so what we have are two conditional intensity functions that give you, for red and for blue, how fast do you expect red events to happen at every point in time, and how fast do you expect blue events to happen at every point in time. And so here's an example that I just pulled out of the air. Just drew a line on a graph. Say a red event happened. Now, this is where this differs from a Poisson process, because Poisson processes have independent increments. These are conditioned on history. So now we have a red event in the history. We condition on it, and our expectation about the future changes. And you can see that given that a red event happened, what I expect red things to do in the future just changed, but blue stayed the same. Now the red event happens, we update what we expect to happen, and so on. Blue event happens, we update. And you could generate all the data, and then you could draw the conditional intensity at every time, given everything that happened before. Now, this illustrated two things going on with this representation. First, the behavior of the reds is characterized just by the red curve, and the behavior of the blues is characterized by the blue curve, so I can specify them independently. And the second is that the blue curve didn't change when red events happen. So the occurrence of blue events is independent of reds in the past. So we have a way of characterizing our temporal conditional independence. So we have this representation, and what we'd like to do is learn these representations from data. And in order to do learning, we need to make a modeling assumption. And the assumption we make is that the conditional intensities are piecewise constant. Now, for a large class of smooth functions, you can approximate them arbitrarily closely with piecewise constant functions. So this is kind of nice modeling assumption to make. So how can we learn a piecewise constant conditional intensity function from data? Well, we're going to do it in two steps. First, imagine a genie told me what regions of time the intensities were constant in. In other words, when was it switching? Say they colored in the timeline for me. Then all I have to do is figure out what should the rate for red be in the yellow region, and what should the rate for red be in the green region. Now that's a somewhat easier problem, right? Just count up the number of reds in yellow, divide by the duration of yellow, and that should give you a pretty good estimate. And in fact, you can choose a conjugate prior for the likelihood of this process that gives you exactly that, right? With smoothing, of course. So now, how do I come up with the coloring? Well, we can push this a little further. Now, I'm going to use the symbol S to indicate a function that colors the timeline, because that defines the structure of our model. Once you give me the structure, I just showed you how to estimate the parameters. Now, we can put a prior on structures, i.e. ways of coloring the line. And if we choose the prior carefully, we can actually get a closed form for the probability of the coloring given the data. Well, not quite, up to a constant factor. But this is good enough, because if you give me two different colorings, now I can just compare the probabilities of both of them and pick the more likely one. And this is exactly what we're going to do. We're going to start out with a basis set of colorings. And what I mean by a basis is I'm going to start combining this, but I want to show you what these do. So the first guy, it says, I'm going to color the timeline dark if there was a red event up to a second ago. So the first red event happens, and we start coloring. A second after the burst of red, we stop coloring, and we start again when another red one happens, and so on. The second guy is the same, just shifted over by a second. The third guy looks at blue, and so does the fourth. And so these are 4 different colorings of the timeline. And now what I can do is say, if I want to predict reds, which coloring is most useful based on the Bayesian score that I told you a couple of slides ago. And I picked the best one. Now, I can go one step further. This is a function with 2 values, right? I can think of it as a binary decision stub. Right? If this function equals 1, take the colored leaf, otherwise take the uncolored leaf. And I can use this decision stump to color the timeline. Well, if the decision stump, I can start splitting the leaves and building a tree. And so I can take another function, so say the blue one, and I can use this to split that leaf. Well, what does this mean? Wait, hold up. The blue one, the blue function, is a function of blue events in the history. And what I'm going to do is color the timeline using blue events in the history, and then see, does that coloring help me predict red ones? Right? So it's saying, do blue events in the history affect red events in the future? Anyways, how do I split this state? I look at the overlap between the red crosshatches and the blue regions. That splits that state. And now, once again, I can look at the score of this coloring. I can choose a different split and look at the score of that coloring and choose the better one. And so I can greedily build up a tree this way, and that completely specifies my model. So here's a completely specified simple toy model. The idea is we have 3 kinds of events, A, B, and C. They're all bursty. When one happens, it'll keep going for a while. The A's triggers the B's, and the B's trigger the C's. And you can specify these with decision trees. I'm not going to walk you through the trees. And so the first thing we did was We generated data from this model and then saw whether we could learn it back, and of course we could. But what's more interesting is, remember the data center example I started with. Say we had a bunch of event logs, which we did. We can train one of these trees for each kind of message that we log. And now we care about the send tech event. So we look at the tree for sending a technician. Now all you need to remember about this tree is it has 4 leaves. And what we're going to do is we're going to go to 3 p.m., apply that tree, and see which leaf we end up at 3 p.m. Turned out to be the red one in the far right. Now we walk up the tree and say, what events in the past made me color the timeline red there? Those 2 guys. And those are the events that now influence my decision to send a technician. Great. So we can build a model from data, and we can use it to understand what's going on in our data. Next step is we want to do forecasting. Now the challenge is that there's a continuous time model, so there doesn't happen to be a closed form way to do estimates of what's going to happen in the future. Right? What we want to do is say, I care about some future outcome, say the user searches for healthcare. What's the probability of that happening? Well, the nice thing about these models is they're really efficient to sample from. So what I do is I sample possible futures, sample a bunch of them, and just count what proportion of those possible futures does the outcome I care about happen. So if we go back to that toy example, remember A's triggers B's, B's triggers C's, and ask what's the probability of seeing a C in the first second, I can sample the hell out of it and find out what the right estimate is, and it happens to be 3 to the minus 3, or 3 times 10 to the minus 3. Well, the problem is that it takes a really long time to converge. In fact, for the first 100 samples, we never see that event happening. Right? So our estimate of the probability is 0. And even after it starts happening, the variances are huge. And this is a standard problem. If the desired outcome is rare, then sampling doesn't do so well. And the standard solution is to do, or one of the standard solutions is to do importance sampling. The idea is you sample from a different distribution where the outcome you care about is more likely, and then you see what proportion of those outcomes, those samples have the outcome you care about. You just reweight the samples to correct for the fact that you sample from a different proposal distribution. So the challenge is to define a proposal distribution P tilde such that the outcome you care about becomes more likely, where you can still compute the correction factor that you need. Turns out with our models it's really easy. Say that you cared about some label L in the first second. Just take your model and boost the intensity of the label L during the first second, as long as the outcome L hasn't happened yet. So what I did was I took a piecewise constant intensity, added a piecewise constant function to it, so I'm still piecewise constant. My sampling algorithm still works, and it turns out that I can compute the correction exactly. So here was the result from forward sampling. Use the importance sampling, and you converge much faster, and the variances are lower. So back to the second problem I was telling you about. Which of these users is going to search for health and wellness related things on the internet so that we can advertise to them? Well, so I actually pulled these examples out of the logs. These are actual test cases that I ran against. And this was a precision recall when over, I think, tens of thousands of users over about a month. And you can see that taking advantage of this temporal dynamics actually gives us much better classification. So just some words about what we're doing now is, so imagine you have what we've done is been able to build models of these worlds where events happen over time. And there's some problems where you want to plan to act in this world. So for example, one of the applications we're looking at is app usage on cell phones. When people use apps on the cell phone, it takes a while to load up an app, so you'd want to pre-cache them. And so there's a planning problem about when do you want to load up or preload apps for a user. And it's important not only to know what app to load up, but when to load them up. And so we're trying to develop planning algorithms for this setting. The other is, I showed you the basis functions, those little, we're on if a blue event happened in the last second or between the second and 2 seconds ago. our models are completely dependent on the right choice of those basis functions. Because once you have the basis functions, we build trees based on them, and we get estimators, right? Well, what is the right set? Can we come up with a set such that we can approximate any conditional intensity? And that's another direction that we're looking at. That's it. Thank you.
Okay, any questions?
So you assume that the labels are independent, but in most real-world scenarios, they're extremely dependent.
No. I don't assume that the labels are independent. I'm assuming that given the history of all the labels, I want to know the intensity of a particular target label.
But I thought you said, like, for example, we have the red, right? And the red and the blue, right? The blue didn't predict the red.
So in that example, I wanted to get across that I could represent independence. But in general, what happens is I might ask a question about red when I'm trying to predict blue.
So you have the complete.
I have the complete, and that's why we can do the health and wellness queries. In fact, one of the slides that I actually dropped was we can predict whether a user who has never been interested in health and wellness before will be in the next week, which is actually arguably...
Okay, but how do you model that? Because the space is very large, right? It's all different...
Right, so we have to actually do the exhaustive search over all other labels. And for queries, what we do is we actually use features of the queries and not the queries themselves.
Any more questions?
I had a question about the very beginning when you talked about the inappropriateness of standard sort of fixed slice models like in markup models for the
I wouldn't word it that way. I think that's a little too strong, but
I guess the question is, I mean, from just a practical perspective, one could have the delta, you do know the time between
yep.
events, and that could be an observation to be placed.
Sure.
And so it's no longer the case that it's a sort of a temporal markup assumption, it would be an event markup assumption for any of those kinds of models. So why would that be not approach?
Event Markov would be maybe a little strong, right? You could.
It could be of whatever order you want.
Right, it could be of whatever order you want. And in fact, you could do that.
In fact, in that case, one could use, for example...
And I think it would,
technology.
at least one way of doing that would reduce to the same thing. Right? And once you do that, it turns out that you don't need to discretize time anyways. But I think that in practice, that distinction may not be as important. So it's a way of being able to separate out the timing of how you step forward in a DBN, if you will, with the resolution of the questions that you ask about the past.
Any other questions?
Is there any role for classifiers here? Because I was looking at your two users, and I immediately classified the top guy as a gun nut.
So if you know ahead of time what classification task that you have, a particular classification task that you care about, that's definitely a way to go. The setting I'm looking at is where we want to query for arbitrary future outcomes. So we have a model. So think of graphical models as opposed to classifiers in the non-temporal world. And so I'm looking at a generalization of, say, graphical models to temporal event streams. But of course, you could build classifiers. And in fact, during the forecasting, you could think of as a particular classifier.
Time for one more question.
Since you're doing it unsupervised, could you at least optimize for some kind of query resolution? So, would you make a model more complex or more, put a model that would predict better in some search feature? Is there some kind of resolution that equivalence of queries that you can optimize for?
So I guess so you could wrap this whole thing. So what we did was training based on likelihood, right? And you could wrap whatever loss function you cared into it. Or penalty function, yeah.
Okay. Well, thanks, speaker.